Hi students, in this session we are going to discuss about the topic reconstruction of a signal from its samples. That is how to reconstruct the original signal from its sample version. Okay, simply we explain this by the concept data reconstruction. Data reconstruction, that is getting the original signal from its sample version. Okay, see, that is nothing but data reconstruction, the process of obtaining the analog signal x of t, that is the original signal x of t, from the sampled signal x s of t is called data reconstruction or interpolation So here we have to obtain the original input signal from the sampled signal. So this process is nothing but data reconstruction, or it may be called as interpolation. Data reconstruction or interpolation. So the process of obtaining the original analog signal x of t from the sampled signal xs of t is called data reconstruction or interpolation. Both are same. Here the original signal I am representing with x of t, and the sampled signal, sampled version. Okay, so after sampling, what the output I will get, that is represented with xs of t. Okay, if the input signal x of t is sampled and it is given an output, and the sample signal output is taken as xs of t, I am considering the sampled signal as xs of t and the input signal as original signal as x of t. Okay, and we know that the sample signal xs of t will be given by multiplying the input signal with an impulse train. Okay, so already I explained you the sampling techniques, how the sampling will be done. So sampling will be done in three ways: by using impulse sampling, or natural sampling, or flat top sampling. Okay, so there I will multiply the input signal, that is the message signal, with an impulse train or a pulse train. Okay, so by that I can get the sample version. See, here I am representing the sample signal as xs of t, that is output signal. Okay, from this is the sample signal of the given signal x of t. Now from x of t I want to get the sample signal. How can I get? I have to multiply that x of t with an impulse train, So by multiplying the given message signal of the input signal x of t with an impulse train, then I get the sample version of the signal. Here the sample version of the signal is taken as xs of t. So I have to write the equation as xs of t will be equal to x of t, that is the input signal, into del t of t, that is the impulse train with period t, capital T. Okay, so if you multiply these two, I will get the sample signal. Okay, and I know the equation of this impulse train also, that is nothing but summation n equal to minus infinity del of t minus n capital T. So substitute that equation in the place of impulse train, that is x of t. So xs of t will be equal to x of t into, so the impulse train equation is, we have the impulse train, that equation is summation n equal to minus infinity del of t minus small n into capital T. Now the sample signal xs of t will be equal to, observe this equation, this is a del function, impulse function. Now this impulse function will have the value only at t equal to nt, if t equal to n into capital T, then both are same and it will be 0, del of 0 equal to 1, we have the value. Other than that one, that is if the value of t is not n into capital T, other than that one, then we will get a value inside the brackets other than 0, the del of 1, del of 9, whatever it may be. So all those values x 0, the function is 0. So 0 into anything is 0. That is, here the del of t minus n into capital T will have the value only at the small t will be equal to n into capital T. So for that reason I am bringing this x of t inside and I am replacing t with small n into capital T. Okay, simple, because for all other values of t this is 0, so hence the total value will be 0. So this will, for this I get the output only at t equal to small n into capital T. Hence I am bringing this x of t inside and I am replacing t with x of small n into capital T. So summation n equal to minus into infinity x of small n into capital T del of t minus small n into capital T. Okay, this one. Now see here the reconstruction filter is assumed to be an linear time invariant system. That is, I am assuming the reconstruction filter. That is reconstruction filter. So I have to reconstruct. I have to reconstruct the original signal. So here the reconstruction filter, which is assumed to be both linear and time variant. Sorry, time invariant. Linear and time invariant. Hence I can write as LTA system. Okay. So here the reconstruction filter I am assumed to be an linear time invariant system, and that has an unit impulse response as h of t. That linear time invariant system has a unit impulse response as h of t. Okay, here the reconstruction filter I am assuming it is both linear and time invariant. So it is a linear time invariant system and it is having a unit impulse response h of t. Now the reconstruction filter output. So I consider reconstruction filter whose impulse response is h of t. Now I need the output of that reconstruction filter. So the reconstruction filter output y of t is given by simple convolution. So I know the impulse response. So the convolution of that input signal to that one and the impulse response will give the output. So here simple, first I had taken an input signal and that is multiplied with the impulse train, and that is produced an output sample version that I treated as xs of t. Now from xs of t, that is sample signal, I have to collect the original analog signal, original data. Okay, so that will be taken place by the help of a reconstruction filter. Here I had considered reconstruction filter which is both linear and time invariant and having a unit impulse response h of t. So for that reconstruction filter, the input will be the sample signal. That is, from the sample signal I have to reconstruct the original data. So for that reconstruction filter I have to give the sample signal xs of t as input. So for this reconstruction filter I am giving this xs of t as input. From this I have to get this x of t, original signal, and the reconstruction filter has an unit impulse response h of t. Okay, now how can I get the output of that reconstruction filter? So for a system having an impulse response h of t and having an input x of t, then output will be equal to x of t convolution h of t. Here the input of that reconstruction filter is xs of t. Sample signal is the input and the system unit impulse response is h of t. So the output of the system will be equal to the convolution of this xs of t and h of t. So here the reconstruction filter output y of t is given by the convolution of this xs of t and h of t. So the output of the one y of t will be equal to convolution formula, integral minus into infinity xs of t. So xs of t is nothing but summation n equal to minus into infinity x of nt del of t minus nt. So you have to write del of t minus nt. Use the convolution formula. So in the convolution formula, the x of t is replaced with x of tau. Here we have del of t minus nt. So this del of t is replaced with del of tau. Okay. So summation. So I am applying the convolution formula to this. This is one signal and another one is h of t. H of t is the another signal. So for these two I am convoluting for this xs of t. So xs of t equation is this one, and the next is impulse response h of t. For these two I am applying the convolution formula. So convolution formula is integral minus into infinity. So first in the first signal, in place of t I have to write tau. So summation n equal to minus into infinity x of n into capital T del of, in place of small t I have to write tau. So del of tau minus small n into capital T into the h of t will be written as h of t minus tau. That is a formula, convolution formula, you all know that. So h of t minus tau d tau. Okay, now changing the order of integration and summation. Now I will change the order of integration and summation. So how can I get the output? Now the output, that is y of t will be equal to, so first I am writing the summation n equal to minus into infinity x of n into capital T. Now I am bringing the integration here. So integral minus into infinity del of lambda minus n tau h of t minus tau, h of t minus tau, okay, d tau. Clear? So simple. Here we have to consider this one. Y of t will be equal to summation n equal to minus infinity x of n t. So see this one. Simply this del of tau minus nt or lambda minus nt, what it may be, you can call that as it is. Okay. Now this will have the value only at this will be equal to nt. This lambda tau will be equal to nt. Clear? Now this one, if this is nt minus nt, so 0, del of 0 is 1, and I will get the value of h of t minus lambda. That is, for this the value should be equal to n into capital T. For this the value should be equal to n into capital T. Okay. So for values from minus into infinity, only I will get at this, if I substitute n into capital T, then I get this as del of 0 equal to 1 into this value will be given that value. So here I have to replace this with n into capital T. So I will get y of t equal to summation n equal to minus into infinity x of n into t, and the value of this one is h of t minus n into capital T, because this will be having a value of 1 only if I replace this with n into capital T. So it means this also I have to replace with n into capital T. So these two I have to replace with n into capital T. Then only I will have. For all other values of this, the value is 0. Anything is 0. So I won't consider the remaining values. I will consider only one value, that is n into capital T. So I will substitute n into capital T at this place and at this place. So this is 1 and this is h of t minus n into capital T. So with this I will get the value of y of t. So finally the output of the reconstruction filter got as y of t equal to summation n equal to minus into infinity x of n into capital T, h of t minus n into capital T. Okay. From this we will see how to get the signal x of t. From this we will see how to get the signal x of t. So that is done by using ideal reconstruction filter. Ideal reconstruction filter. Okay. Here we have to choose that the sample signal of frequency fs should be greater than 2 fm, that is twice the maximum or the highest frequency component of the message signal. Then only I can get the reconstruction signal. We all know that. So based on all those assumptions, I am choosing a ideal reconstruction filter. I am choosing a ideal reconstruction filter as, let us choose bandwidth of the ideal reconstruction filter as 0.5 fs. I am choosing the bandwidth of the ideal reconstruction filter as 0.5 fsc. Here I am explaining this concept with respect to the frequency, sampling frequency. Okay, sampling frequency fs. I am explaining all this with respect to the sampling frequency fs. So I am choosing bandwidth of this ideal reconstruction filter as 0.5 fs. Now the transfer function. Now the transfer function of this ideal reconstruction filter is, I need the transfer function. So transfer function is actually generally represented with h of omega, but here I am explaining with respect to the frequency f, so I am writing as h of f. Generally we will write h of omega. Okay, actually omega equal to 2 pi f, we all know that. So here I am explaining with respect to f, so remember that one. Now the transfer function of that ideal reconstruction filter is h of f equal to capital T, h of f equal to capital T for mod f less than 0.5 fs, that is fs by 2, that is if the frequency value is from minus fs by 2 to plus fs by 2, then the value of this transfer function is capital T, and in other cases that is 0. So see the diagram, you will get a clear idea about this. So this is an ideal reconstruction filter whose transfer function is like this. So from minus fs by 2 to plus fs by 2, the value of this transfer function h of f is equal to capital T. So from minus fs by 2 to plus fs by 2, the value of this transfer function is equal to capital T, and in all other frequencies the value is 0. So I am considering this the transfer function of IR of ideal reconstruction filter as h of f equal to t for minus fs by 2 to plus fs by 2. In all the remaining cases it is 0. Okay. Now, for this ideal reconstruction filter, I have to give the input. That is the sample version. That is the sampled version. Okay. So, the sample version is xs of t. This is the sample xs of t. So I am giving this as an input. So xs of t is summation n equal to minus infinity x of nt del of t minus nt. So summation n equal to minus infinity x of n capital T into del of t minus. So I given the sample signal as input to this ideal reconstruction filter, ideal perfect reconstruction filter, and it has to produce the original signal as output, that is x of t. See here h of t will be equal to, so I have h of f, in that I need the h of t. The h of t will be given as integral minus fs by 2 to plus fs by 2. Okay, so that is I am getting the inverse transform. I am applying the inverse transform. So h of t will be equal to integral minus fs by 2 to fs by 2 into t. So this is area of t into e power j 2 pi f t. Simply we have to, generally we will write e power j omega t. Here I am writing e power j 2 pi f t. Simply why? Because up to now we consider with respect to omega. Here I consider with respect to f. So from this I can write h of t will be equal to integral minus fs by 2 to plus fs by 2 capital T into e power j 2 pi f t. 2 pi f t, that is like omega t, j 2 pi f t df. So we are differentiating with respect to frequency. There I will go with respect to omega. So in the inverse transform formula we will use d omega like that. Here it is with respect to frequency. I am using the formula of df. Simply instead of omega I am writing f. So the formula will be like this. So h of t will be equal to integral minus fs by 2 to plus fs by 2 into capital T e power j 2 pi f t dt. Now see h of t will be equal to, so bring t outside because we are differentiating with integrating with respect to f. So bring t as outside. Now integrate this one with respect to f. So e power j 2 pi f t by j 2 pi t, because we are differentiating with integrating with respect to f. So j 2 pi t. So that will be equal to t by j 2 pi t. T by j 2 pi t into j 2 pi t. So I am bringing this one j 2 pi t into, so this is the one which will have to e power j 2 pi f t. So substitute the limits. In place of f we have to substitute the limits. Okay, now we will get this one. Finally 1 by pi fst. So this from this I can write t equal to 1 by fs. T equal to 1 by fs. So 1 by fs pi t, and I brought this 2j inside, simple. Okay, so if I brought this inside, so the equation e to the power of j pi fst minus e power minus j pi fst by 2j. Okay, see this, first I had gone for h of t, so I brought t outside. Okay, I brought t outside and I gone for the integration of this one. You all know the integration, so that value divided by j 2 pi t. Now I substitute the values fs by 2 in place of f. So what happens, 2 gets cancelled and I get e power j pi fst, e power minus j pi fst. Substitute the values and 2 gets cancelled. I got this value. Now in this t equal to 1 by s, we all know that frequency and time beta are inversely proportional. So I substitute 1 by fs and pi t, I kept it. I brought 2j inside. Why I brought 2j inside means this is a formula. This is the formula for sin pi fst. E power j theta minus e power minus j theta by 2j. E power j theta minus e power minus j theta by 2j will give sin theta. Using that formula I am writing this as sin pi fst by pi fst. Sin pi fst. So this place I have to write sin pi fst. So here I already have pi fst. So sin pi fst by pi fst is nothing but a sinc function. So I am writing in terms of sinc function. We all know the sinc function. So I am writing in terms of sinc function. Now substitute this value of h of t. Substitute this value of h of t in the output. What I got, y of t. So there in the above, in this equation that is substitute y of t in the expression of the output y of t. Substitute this h of t value in the expression of y of t. Okay, now y of t will be equal to x of t. Y of t will be equal to x of t. Why? Because the output of this one is our original signal. So this is also output of the reconstruction filter. The output of the reconstruction filter is our original signal x of t. Hence I have to write this output as x of t. Simple logic. So here this is the output of the reconstruction filter. So output of the reconstruction filter is our original signal x of t. Hence I have written y of t equal to x of t, and that will be equal to summation n equal to minus infinity x of nt. Here I have h of t minus nt, and I have got the value of h of t as sinc fst. Okay, now in place of t I have to go for t minus nt. So in place of t I have to substitute t minus nt. So sinc fs into t minus n into capital T. So here if I bring t outside, so that is 1 by fs. 1 by fs gets cancelled. So I will get small t by capital T minus n. So summation n equal to minus infinity x of n into capital T sinc. So here I brought t as outside of this one, make it as common. So this will become small t by capital T, and outside t is nothing but 1 by fs. 1 by fs, this fs cancels, so that will be equal to small t by capital T minus n. So this is the general form what we use. Generally, regularly we will use this form of representation. So the original data is reconstructed from this, because x of t is the original data. So the original data is reconstructed from the above equation. So by using the above equation, I can recollect the original data. So the original data will be reconstructed perfectly. Okay. Now this filter, actually here this filter is non-causal filter, and it impulse response is not limited. See here I consider the impulse response as h of t, and it is a non-causal. The filter that I had taken is a non-causal one, and the impulse response is not limited. So it is not used for real-time applications. So in general practice we can't use these type of filters. This is ideal, it is perfect. So practically no one is perfect. Okay, hence we can't use this type of filters for real-time applications. Why? Because simply this filter is non-causal and the impulse response is not limited. So this filter is not used for the real-time applications. So that in practice, in real time, that is in practice, we use other method of filters, other filter methods. We use other methods like zero hole method, first order hole method, and linear interpolation. So in practice we will use most commonly we will use three methods like zero order hold, first order hold, and next linear interpolation. Zero order hold, first order hold, linear interpolation. In these three, the most commonly used one is zero order hold. So in practice, in real time, generally most commonly we will use zero order hold. Okay, so this is the explanation about how to reconstruct the signal from the sample version. That is reconstruction of the original signal, analog signal from the sample signal. Okay, I hope you are all clear with this. Okay, simple here. First, I have taken the sample signal. Okay, how can I get the sample signal? By multiplying the message signal with an impulse train. So just by multiplying the message signal with an impulse train, I get the sample signal. Okay, now after that I use then reconstruction filter with unit impulse response h of t. So we all know the output of that one will be nothing but input of that filter, reconstruction filter, and the impulse response. So that for that filter the input is sample signal. So I had gone for the formula of convolution. I changed the order of integration summation. Here I got a value of h of t minus nt. For this I had taken an ideal reconstruction filter with some assumptions as bandwidth as 0.5 fs and the transfer function as like this. So there I got the h of t value as sinc fs of t. So using that h of t in this equation, so I substituted h of t in this equation. Finally I got the original reconstructed signal. That is output of the reconstruction filter is nothing but the input x of t, input signal x of t. So by substituting this h of t in this equation, I get the original signal. So the original data is reconstructed, but this filter is non-causal and impulse response is not limited, so it is not used for real-time applications. So in practice generally we will use three important methods, that are zero hold method, zero order hold, next one first order hold, and last I will go for linear interpolation. In these three, most commonly used one is zero order hold. This is today's class. Okay, I will go for the remaining topics in the next class. Thank you one and all.